Hi friends, in this video I'd like to show you simple ways to implement time evolution in Qiskit. Uh, Specifically I'm gonna cover a little recap of time evolutions in quantum mechanics, and then I'm gonna show to you how to implement that concept in Qiskit. Of course, I need to assume that you are somewhat familiar with the basic theory of quantum mechanics, and we're gonna go through. My plan is gonna go through some examples, which are gonna make hopefully clear how to implement such things in Qiskit. In the next video, I plan to show you how to get the state vector of a quantum circuit. Maybe you're a physicist or a researcher interested in simulating a quantum system using Qiskit, and would like to get some expectation values, and the state of the circuit is of course very appropriate for that. I'm going to show you how to do this kind of stuff in Qiskit 2 in another video. But okay, consider first a closed system whose state vector at t equals 0 is just size 0 as usual. And we know from quantum mechanics that we can construct, given a Hamiltonian operator h, a time evolution operator u of t, such that when I apply u of t to size 0, I get the state of the system at time t, which is of course psi t. This operator, or this gate, I can already call it a gate, has to be unitary because it has to take a quantum state into another quantum state. So the norm of the quantum states must be preserved, and this condition is equivalent to say that u times its transpose conjugate, its Hermitian conjugate, is the identity. But we don't need to get this technical detail here. We need only to recall that if h is time independent, we can show that u takes this simple form, the exponential of an operator. And again, if you're not familiar with such concepts, I'd like to refer you to the standard graduate level textbook from J.J. Sakurai, which covered this topic in great detail. Or if you'd like to go faster, I can recommend you to my master thesis, whose link I'm gonna put here below in the description. Okay. But another way to, if our system is a single qubit, another way to state how time evolutions work is to say that if the initial state is this vector here in the Bloch sphere, actually a quantum computer is a machine that rotates qubits into their within their Bloch sphere. The operator u of course takes this state psi 0 into another state of the Bloch sphere. Of course, all qubit states lie on the surface of this figure. And for instance, but how to implement that in Qiskit? The first thing to know is that Qiskit only accepts symbolic expressions when they are written in terms of the Pauli basis. Okay. If you're more familiar with the sigma notation, I recommend you to get used to this standard notation of quantum computing if you would like to know more, to study quantum computer in further detail. We call this is of course the identity operator, and we call the sigma x, sigma y, and sigma z Pauli matrices as the x, y, and z gates. Okay, we're gonna apply them to quantum circuits. The good news is that any operator a can be expressed in terms of the Pauli basis. This is why it's called Pauli basis. So any operator you wish can be implemented in your quantum circuit. But first you need to convert its expression to a linear combination of this form here. And of course, if you have, for example, a system containing 2 qubits, you can form tensor products of this basis here, and those tensor products are also a basis for the space of 4x4 matrices, and so on. Okay, but this is a technical detail. I'm just mentioning to you so that you can know that this is something always achievable. Okay. In the examples I'm gonna cover, I'm gonna use qubit states of the harmonic oscillator, And I would like to recall that in the ladder operator formulation of the harmonic oscillator, we have this operator A here, which lowers the state of my oscillator by 1 unit, and its complex, its Hermitian, conjugate, which raises the state of my oscillator by 1 unit. If I restrict myself to the subspace spanned by the vectors 0 and 1, the ground state of the harmonic oscillator and the first excited state, of course all qubits can lie within this subspace, I can construct the matrix representing A within this subspace in the usual way of quantum mechanics by taking inner products here, and I can construct also the matrix representing A dagger in this same subspace. Of course, I could simply take the Hermitian conjugate of this expression right above. But the point is that you can check that these operators can be written as these linear combinations involving the X and the Y gates. This is going to be very useful for us in a second. Okay. But last, the Hamiltonian, we can see too that the Hamiltonian and the time evolution operators take this simple form. Of course, in standard textbooks, you're going to find this Hamiltonian with another additional term of 1.5 here, but I'm just setting the energy reference level to the energy of the ground state, so this is an acceptable Hamiltonian as well. Okay, so let's take a look of how to implement those concepts in Qiskit. First, let's look at this code snippet here of a 1-qubit circuit. First, I need to import my libraries and my functions, from the standard libraries. I need to import actually the quantum circuit function from Qiskit, and I'm going to import here from Qiskit.opflow, which is a library containing many useful tools to deal with operator classes and instances in Python. I'm going to import the X and Y gates from that, and the ladder operators are very easy to write. I can write them symbolically directly using the linear combinations I presented to you in the former slide. And the Hamiltonian and time evolution operators are implemented also directly. H is simply A dagger times A. This is a very useful way of multiplying two matrices. In Python, I don't know if you know, but in Python there is no standard built-in function to multiply two matrices together. So in Qiskit.opflow there is this at operation here, which is very helpful. And the time evolution operator, of course, needs this parameter omega t, this dimensionless parameter, which I'm going to set to 1, but if you can set to any value you wish. And U can be obtained by simply taking this exponential I instance in Python and passing h times omega t as an argument. Okay, this function here actually returns the negative complex exponential of its argument. Okay, then we can create a 1-qubit quantum circuit, of course, and use this unitary function to apply U. We pass U here as an argument to the qubit 0. Okay, there's only 1 qubit in our circuit, so we need to specify the qubit simply as a single number. But if there were, I'm going to cover that in a second, but if there were 2 qubits, actually we would have to pass a list here as an argument. So I'm going to see that in a second. This third argument here is optional. It's just a label in order to make a drawing of our circuit. So here it is. We can see that, okay, we could indeed apply this unitary U to our circuit. And of course, I'd like to make some checks to know if my results are right. That's why I chose to implement qubit states of the harmonic oscillator. They are well known. And I'm going to do that in the next video when I'm going to present you how to get the state vector of a circuit. I'm going to calculate expectation values of this Hamiltonian right here and confirm that my time evolution went indeed right. Okay, but what if I would like to evolve a 2-qubit quantum circuit? I can proceed at the beginning of the code the same way as before, but then I have to make a little modification in section here regarding the Hamiltonian of the system. So I'm going to suppose that I wish to evolve 2 qubits of the harmonic oscillator. So I'm setting the Hamiltonian of a single harmonic oscillator qubit here as this HHO. Okay, it's the same expression as before. But now I'm going to construct a composite Hamiltonian here by taking the tensor product of HHO with itself. And tensor products in Qiskit upflow can be implemented by using this little hat here operation, which is also very helpful. Again, I can construct U the same way as before, and I can evolve this 2 qubit circuit, which I define here, the same way as before. But here in the unitary function, I need to make a little modification. I need to pass the qubits 0 and 1 in my as an argument. As I need to pass them actually as a list, a Python list. Okay. And okay, here it is, our circuit. The UT is applied to 0 and 1. If I'd like, for example, to evolve only qubit 0 in time, I could just comment this line here, making the composite Hamiltonian, and just passing just 0 here as an argument, just as before. I can define actually 2 qubit circuit, but evolving only 1 qubit. This is very natural and easy to achieve. And finally, if you have, for example, if you are not interested in implementing the Hamiltonian of your system or time evolution operator in terms of the Pauli gates actually, and you have an explicit expression, matrix expression of your operator, you can just set that by brute force, in Python, write that directly and use the same unitary function to apply that to your quantum circuit. So here it's a simple example. I've taken that from the Qiskit documentation, I think, and again you have the same results to your quantum circuit. And again, in the next video, I'm planning to show you how to get the state vector of your quantum circuit, and there I'm going to go back to these code snippets and confirm that we got the right results by calculating the expectation value of the Hamiltonian of the system, in order to confirm that we have indeed the energy, the expected energy levels for the harmonic oscillator. So stay tuned in the next videos. Thank you very much.